This is section 11.2, where we were continuing our discussion of sequences and series. Now we're looking at two specific types of sequences in this section and the following section. We're going to look in this section at a group called the arithmetic sequences. Now I'm sure the word looks like arithmetic, but remember that if it is an adjective, as it is describing the sequence here, we pronounce it as arithmetic. And that's going to have a specific definition, and we're going to look at some of the rules and analysis techniques for these types of sequences. And then we'll follow up with the next section talking about geometric sequences. So let's talk about, first of all, what is an arithmetic sequence? An arithmetic sequence is a specific type of sequence where each term differs from the previous term by a constant amount. In other words, to get to the next term, we add the same number over and over again. This constant is called the common difference, and is usually going to be denoted by D for difference. Now remember, difference means if you were to subtract two things. Now if you subtract a term minus its previous term in a sequence, you're going to get a constant amount if that sequence is arithmetic. So this right here is an example of an arithmetic sequence, because 1, 3, 5, 7, 9. What's the difference between each two terms? 1, 3, a difference of 2, right? 3 minus 1 is 2. 5 minus 3 is 2. 7 minus 5 is 2. 9 minus 7 is 2. So the common difference is 2, because that's what you get when you subtract a term minus its previous term. And you got to do it in that order, all right? Because what's the common difference here? 5, 1, negative 3, negative 4, negative 11, negative 5. What's 1 minus 5? That's negative 4. Negative 3 minus 1 is also negative 4. That common difference is the number you're adding to each term to get to the next one. 5 add a negative 4, you get 1. Minus 4 is minus 3. Minus 4 is minus 7. So the common difference is negative 4. Now we have a formula for the general nth term of an arithmetic sequence. And just so you know, whenever I use that terminology, nth term is just a way of saying the general term for the place, the n position in that sequence, right? So first would be, we write first as first, second, third, but after that they're all written with a th, right? Fourth, fifth, sixth, and so on. So if I'm going to talk about, once I get to an arbitrary place in the list that I want to describe as n, I'm going to call it the nth term. That's why I mean this. Now, that said, the formula for that on an arithmetic sequence is always the same. The a sub n is the first term, a sub 1, plus n minus 1 times d. So if I wanted to find the expression for the nth term of an arithmetic sequence such that a sub 1 is negative 4 and d is 3, I can do that using this formula right here. Now, just so that you understand, what does this sequence actually look like? I'm not asking you to find that here, but just so you can identify some terminology and be comfortable with what I'm saying, what is the sequence that starts at negative 4, that's the first term, and has a common difference of 3, meaning it's arithmetic? Negative 4, the next term would be, you add 3 to it, you get negative 1. Add 3 to that, you get 2. Add 3 to that, you get 5. Add 3 to that, you get 8. And so on. That's the sequence. We want to find a formula so that if I plug in 1, I get negative 4. If I plug in 2, I get negative 1. If I plug in 5, since I want the fifth term, I would get 8. So I use this formula here. Just plug in what I know. A sub n is what I want to find. A sub 1 was negative 4 plus n minus 1. N's your variable. A sub n is your output, so it stays there. And then d is known. That's 3. Now all I'm going to do is simplify this. Simplify it by multiplying out the 3. I'll end up with negative 4, okay, plus 3n minus 3. Or if I simplify, I get a sub n is 3n. Negative 4 plus a negative 3 is negative 7. So 3n minus 7. There is your general formula for that sequence. Let's do another just like it with the added problem of finding the 10th term in the sequence. So instead of actually having to find the 10th term by listing out the first 9 to get to the 10th, I can actually use my formula to do that. Because watch this. A sub n is going to be a sub 1 from here, 4 plus n minus 1 times 5. Okay, which is 4 plus 5n minus 5, or a sub n is 5n minus 1. There's your formula for that sequence that starts 4 and then adds 5 each time. Now to find a sub 10, all I have to do is use my formula. That's going to be 5 times 10 minus 1, or 50 minus 1, which means a sub 10 is 49. I know what the 10th term in my sequence is without having to find the first 9, because I knew that it was arithmetic, I knew the common difference, and I knew the starting value. Boom, I can get there. Another type of question that we are often asked to answer when dealing with sequences in series is something called the partial sum, okay, or technically the nth partial sum. Now, all I mean by the nth partial sum is the sum of the first n terms of an arithmetic sequence. So, for example, if I were to write down s sub 1, meaning the first partial sum, that is just the first element of a sequence. S sub 2 is a sub 1 plus a sub 2. It's the sum of the first 2 elements. S sub 3 is a1 plus a2 plus a3. And so forth, right? So the nth partial sum would be what you get if you add up all the way up to whatever n is in your sequence. Now, the nice thing about arithmetic sequences is there's a shortcut formula. I don't actually have to add them all up to get the final answer. Turns out S sub n is always equal to n times the first term of your sequence, call it a sub 1, and the last term of your sequence, up to, if you're finding the nth term, or the nth sum, the last one a sub n, and then divide that all by 2. So in other words, let's take this for example, right? This right here is the sum from n equals 1 to 40, right? Of, in fact, let me say k equals 1 to 40, of just k, right? The sequence is just k going from 1 up to 40. So this is like a partial sum because it is a finite number of terms. It goes up to 40. So S sub 40 in this case would be to find the sum of the first 40 terms of this sequence. So all I got to do is figure out, first of all, how many terms there are. That's the n, and put down 40 there. Then I'm going to take the first, which is 1, plus the last, which is 40, divide that all by 2, and that will add this up for me in one quick step without having to do it manually, one term at a time. Right? I could go to my calculator and add 1 plus 2 plus 3 all the way up into 40, but this is going to get me my answer a lot quicker because I'll get 40 times 41 over 2. You can divide the 2 out of the top and bottom. You'll have 20. 20 times 41, you can bring down the 0. 2 times 1 is 2. 2 times 4 is 8. You get 820. Right? I was able to do that on paper here faster than we could do that in our calculator if we did it term by term. And that's what we can do with this type of formula. So consider the next example. We've got an arithmetic sequence that starts at 12, and after 8 terms we end up at negative 23. We want to find the sum of those terms. Now, by being arithmetic, we know it has a common difference, but the formula doesn't even need the common difference, so we can actually just plug it in. S sub 8, the sum of the 8 terms of the sequence would be 12. Sorry, I should put 8 for the n, the number of terms. 12 plus a negative 23, all divided by 2. That gives me 8 times negative 11 divided by 2. Divide the 2 out of top and bottom. 4 times negative 11, I get a negative 44 as my answer. We've got one last example here that we can answer using the formulas that we've been given so far. Let's say, for example, we have a sequence. This A1 is 12, A8 is negative 23. The question is, what's the common difference? Right? What would I have to add to 12 each time so that after 8 terms I end up at negative 23? Now the quickest way to do that is just to go back to this formula right here, the general sequence term, A1 plus n minus 1 times d. Notice how with these two pieces of information I have everything I need to know in this equation except for d. For example, I could say that if I plugged in 8 for n, that formula looks like this, right? Just let n equal 8. Now the reason I do that is because I know a sub 8. So a sub 8 is negative 23. A sub 1 is 12. 8 minus 1 is 7 times d. I now have a single equation with one unknown. I can solve that for d by subtracting 12 from both sides, which gives me negative 35 is equal to 7d, or divide both sides by 7, gives me that d would be negative 5. I would have to subtract 5 from 12 each time so that after my 8th term I'm at negative 23. Let's look at one last example as an application problem. In this problem we're given that our grandmother has assets of $400,000. One option she is considering involves an adult residential community for a 6-year period beginning in 2006. The model, A sub n is equal to 1800n plus 58,730, describes yearly adult residential community cost in years after 2005. Does your grandmother have enough to pay for the facility? Alright, so let's think about what we have here. This is an arithmetic sequence because it has that form that we saw that arithmetic sequences have, something times n plus some other number. Now because that's arithmetic, because we're adding 1800 each time we go from one year to the next, we can find the sum of an arithmetic sequence using S sub n is equal to n times a1 plus an all over 2. Now we want to know if our grandmother, in this case, has enough to pay for the facility after 6 years. It's a 6-year period. So we want to find S sub 6. Okay? So S sub 6 would be plugging in 6 for n. Now A1 means plug in 1 right here. Right? A1 is 1800 plus 58,730, or 60,530. That's A1. Now what is A6? Right? Because I want to find the last of the 6-year period. So A6 would be 1800 times 6 plus the 58,730, which is 10,800 plus 58,730, or 69,530. Plugging that now in for A6, all of this divided by 2 will give me the sum of those 6 years. So 6 times 60,530 divided by 2, or plus 69,530. You add those up, multiply by 6, divide by 2. In my calculator, I end up with 390,180. So does she have enough? Well, if 400,000 is what she's got to start with, then yes, she clearly has enough funds. We were able to answer that question using our partial sum formula for arithmetic sequences. And that's the end of section 11.2, where we've discussed arithmetic sequences. Now we're ready to talk about another kind of sequence called geometric sequences.